Okay, so now we go on to the periodic table. So I guess before we get to periodic table, let's talk about different types of electromagnetic radiation. Visible light, X-rays, microwaves, in order of increasing wavelength, frequency, energy per photon. I guess wavelength started off. Okay, so wavelength and frequency are inversely proportional. So the longer the wavelength, the higher the frequency, and the I'll say the longer the wavelength, the shorter the frequency, the shorter the wavelength, the higher the frequency. So let's see here. Microwaves have the longest, then visible is the middle, and X-rays are the short as far as wavelength. So it's going to go X-rays, visible, and microwaves for wavelength. Frequency is going to be opposite from low to high. It's going to be microwave, visible, X-rays, and B and C are the same, energy per photon. So the higher the frequency, the more energy. So there we go there. So write the electron configurations for each element. So you find these in the periodic table. Magnesium is a alkaline earth in the third period, and the period is a row. So that means you get neon's configuration. So neon's configuration, and then it'll just be 3s2, like that. And sulfur is also in the third period, so it's just over more, and it has 16 electrons. So you still start with neon's configuration, and then add the electrons up, and then the extra electrons go into the 3p orbitals. And then the last one, gallium, has 31 electrons, so it's in the fourth period. So you put the argon in there, and it's also right below aluminum. So, and don't forget, you have to fill up the entire 3D shell on the way over. And I know it's kind of weird, but the 4s, due to the Zeeman effect, is lower energy than the Ds. So the 4s comes first, then the 3Ds, and then the last electron in one of the p orbitals. So write the electron diagram for silicon. Silicon has 14 electrons, and so with neons you fill it right up. And also, if you haven't noticed, it's going to be the same as carbon. It's underneath carbon, or at least electronic structure. So you fill them up, and then adding the last electrons at the last part, there's something called Hund's rule, where you add electrons in parallel spins and open orbitals. For me, I think of it like I like to swim, and like I like having my own lane. Right? So if there's 3 lanes open in the pool, I would be really angry if someone came in the open pool and decided to jump in my lane and swim with me. I like, hey man, use the open lane. Or even if the person did that, I would probably just swim over the other lane and just swim in that one, kind of thing. All right, fine. If you like this lane so much, I'll take the open lane, kind of thing. So that's Hund's rule. And then also opposite spins, so meaning like that at any given time the total projection of the magnetic field is pointing in the opposite direction of the other electron. So that's what the spin means, kind of sort of among other things. Let's talk about valence and core electrons. So valence electrons are outer electrons and core are inner. And valence specifically are the highest number n, the principal quantum number n. So those are always that. So here is selenium's electronic configuration. And now notice that there are 6 valence electrons. The 4s, there's 2 in the 4s and 4 in the 4p. Even though 3d I know is higher energy in the ground state than the 4s for a non-hydrogen like atom, right? So the 3ds are slightly higher energy. There's still a lower quantum number n. So the 3d n number is lower than the 4s. So because of that, the number of valence electrons include the 4s and not the d's. So remember that. So selenium has 6 valence electrons, just like oxygen. So we can write electrons from the periodic table, and this is an easier way to do it. Now, mind you, there are exceptions to this rule, especially in the transition metal, the D block, so and the F block, and the lanthanides and actinides. So, but this is the general rule. So if you look for arsenic, you can look there. It's the fourth period, and then it has argon's configuration, and then moving over the alkalis and alkaline earths has the s orbitals. The middle block is a d block. The far right block is the p block, and the one disconnected, that's the f block. So moving over, that's going to be 4s squared, 3d10, then 4p3. Moving over, and originally having argons. You can write out argon's configuration, but it's long. You can only do the noble gas configurations in brackets. You can't use any other element for that, by the way. So only the noble gases. So look at atomic size. So as you move from left to right across the periodic table, the atoms get smaller. And these are easier to see when we put it next to the periodic table. So looking at carbon and oxygen, since oxygen is to the right, it's smaller. So carbon is the bigger one, because as you move right across the periodic table, the atoms get smaller. And that's because the effective nuclear charge gets smaller as you move over. So carbon has 6 protons, but it's kind of like a +2 charge because the 2 core electrons shield it, and oxygen sort of has a +6 charge because the 2 of the plus charges are shielded by the internal one. So and electrons are negatively charged, they're drawn more towards the positive center, so it moves as you move to the right, it gets smaller. So carbon's the bigger atom. And lithium or potassium, so as you move down the periodic table in the same column, as you move down, the atom gets bigger, just because there's more shells of it. And so the electron cloud is much bigger, and so for potassium, since it's lower, it's the bigger atom. And now for aluminum and carbon, so carbon is to the right since smaller. It's also higher up, so it's smaller. Or you can look, aluminum is to the left, so it's bigger, and it's also lower on the periodic table in terms of which period, and period is a row. That means that aluminum is the bigger atom. So aluminum is definitely the bigger atom. Now we have selenium and iodine. So this is a little confusing because iodine's to the right, so it looks like it's smaller. Selenium is higher, so it looks like it's smaller. And this is ambiguous because you cannot use the periodic trends to figure this one out. So from that, this indicates then that we don't know. We don't know. So we'd have to look up the data to figure this one out. So first ionization energy, and this is kind of the opposite of the size. So electrons are negatively charged, and it's harder to rip off an electron that's closer to a more positive center. So really, first ionization energy is going to be more or less equal opposite of the atomic size. And this is the first ionization, the first electron. This is to rip the first electron off of the atom. So we'll start off with magnesium or phosphorus. Phosphorus is further to the right, therefore it has a higher first ionization energy. It's a smaller atom, more positive charge. It's harder to rip off the electron, so phosphorus has the higher first ionization energy. And arsenic and antimony, arsenic is higher. It's a smaller atom, therefore it's harder to rip it off, so arsenic has the higher first ionization energy. And nitrogen or silicon. Nitrogen is further to the right, and it's further up, so it's doubly the more going to have a higher first ionization energy, so it's definitely nitrogen. Now oxygen and chlorine, this is one of those we don't know because we're not entirely sure where it is in this because the effects cancel. So we have to look up the actual data to figure that out. We can't figure that out from the just looking at the periodic table. And you can work on those. And thank you for listening.